Okay, so when we compute eigenvalues, the way that we do that is by looking at the characteristic polynomial and finding the roots. And what you should know is that when you are finding the roots of a polynomial with real coefficients, you can still arrive at complex eigenvalues. The canonical example of complex roots. The canonical example of this is x squared plus 1 equals 0, right? The polynomial here, x squared plus 1, has nice coefficients, integer coefficients, in fact. And yet, complex numbers still enter the picture if we want to find the roots of such a polynomial. That's also going to be the case when we go to compute eigenvalues of our matrices, even though all of the entries of our matrices might be real numbers. Okay, we can still get complex eigenvalues out. And the question becomes, how do we then get solutions to our differential equations that are associated with these types of matrices? Well, it's time to find out. And this is going to be a mix of a lot of the ideas that we've talked about in the past with respect to complex numbers and such. So it's going to be a good review of all of that stuff. Complex numbers are super important, so this is well worth the time. And we're going to see interesting phenomena, geometric phenomena, come out of the solutions that we get in the complex case. So let's look at an example just real quick. Let's talk about complex eigenvalues. And here is a very good example. Let's think about the system x prime equals, and we're going to take as our p here 1, 2, negative 1, 1, x. Okay. So as usual, we're going to first find the eigenvalues of x, or p. What's playing the role of p here? I'll write this down. Is this 2 by 2, 1, 2, negative 1, 1. And so we need to find the roots of the polynomial determinant of p minus lambda I. This should be a very familiar story at this point in your life. This is 1 minus lambda, 2, negative 1, 1 minus lambda. And if we take the determinant of this, we get 1 minus lambda squared, whole thing squared, minus negative 2, which is plus 2. All right? And if I expand this out, which I should if I want to find the roots eventually, which is what I want to do next, I'm going to get 1 minus 2 lambda plus lambda squared plus 2. I'm going to erase this parentheses. I don't know why I have parentheses there. It's not necessary. And then this becomes this becomes lambda squared minus 2 lambda plus 3. Okay? Now, one thing that I can do is use the quadratic formula to find the roots of this characteristic polynomial. Of course, that's going to be lambda is equal to 2 plus or minus the square root of negative 2 squared, which is 4, minus 4 times 1 times 3 divided by 2. And this ends up being 1 plus or minus the square root of negative 8 over 2. Now, the square root of negative 8, the square root of a negative number doesn't exist over the real numbers, but it does exist over the complex numbers. And what that ends up being is the square root of 8 times I. Now, square root of 8 we can write as 2 times the square root of 2. So this becomes 1 plus or minus 2 times the square root of 2 over 2 times I. Make sure you understand that. And then I can cancel the 2 upstairs and downstairs, and what I get are 2 roots, 1 plus or minus the square root of 2 times I. Okay? This kind of situation is typical. It is what will always happen, in fact, when your matrix has real coefficients, real entries. Okay? Because anytime you factor or you find the roots of a polynomial, in this case, the polynomial is this one. Anytime you find the roots of a polynomial with real coefficients, the coefficients here are 1, negative 2, and 3, which are hella real. then you're always going to have roots which are either themselves real numbers or which come in complex conjugate pairs. And that's what we see here. We see a pair of real numbers here which are complex conjugates of one another. That always happens. In fact, that's enshrined in a result called the fundamental theorem of algebra. Okay? And you should know this. Okay. So, cool. We've got this complex eigenvalue. So if we wanted to go and write solutions, we could. We could do what we did before. We could find eigenvectors associated with these eigenvalues and go through that whole rigmarole, okay? And we would have to do one for each of the eigenvalues. This is not unlike what we were doing before. However, there is a better way of going about doing this. And I think I'm just going to shove this down your throat, foie gras style, as usual, okay? Here's the idea. In this case, we need to only pay attention to one of the pair of complex conjugate roots. So to solve the system, here's the method. We need to only study one of the above eigenvalues, one of the complex conjugate pair. So remember, I'm saying that in all the situations that you're going to encounter, your complex eigenvalues, when they arise, they will always arise in pairs, complex conjugate pairs. And I'm saying, I'm giving you a certificate saying you're allowed to ignore one of them. Okay, so we're going to take lambda equal to 1 plus square root of 2 times I. Okay, you're allowed to do that. I'm ignoring the negative 1. Okay, all right. Then, next, we are going to find an eigenvector. I don't know what the eigenvector is yet. I haven't computed it yet. But let's just call it V for now. And this V may very well have complex entries in it. Okay? It might very well have complex numbers as the entries in V. Okay? But it's still the case that we can form the solution x equals V e to the lambda t, where again v is a complex complex vector with a vector with complex entries, and lambda is a complex number. And so this is going to be a complex valued solution in general. And I don't know if you remember what we did in the case where we were solving second order homogeneous linear differential equations with constant coefficients, and we arrived at a characteristic polynomial with complex roots. Remember what we did is we ignored one of those roots, just as we're kind of like doing here. We got a complex valued solution, but then we computed the real and imaginary parts of those complex solutions. So the real part is denoted sometimes like this. I'll write re of x and imaginary part of x. Okay? And here's the fact that I'm shoving down your throat, and this is very believable. These are real valued solutions. Not only are they real valued solutions, but they're also linearly independent. Okay? Now, how are we going to find the real part and the imaginary part? Well, this is where we're going to use Euler's formula, okay? It's going to be quite computationally intensive, but you are not children, okay? You can handle a bit of long computation. And if you're particularly deranged and you're maybe you even find this kind of thing enjoyable. Okay, so let's see how this all works. Let's go back to our example, and let's study this eigenvalue 1 plus square root of 2 times I. And what we want to try to do is find a complex eigenvector whose eigenvalue is 1 plus square root of 2 times I. All right, so we're going to examine, let's see, I'll do this in green. No, I'll do it in green. So lambda equals 1 plus square root of 2 times I. So if we look at what we want to solve, remember, we want to solve now the system. We want to know when P minus this lambda times the identity times V is equal to the 0 vector. We want to find non-zero V, which make this happen. If we can find such a V, that's an eigenvector. Well, what is P minus lambda times I? So in this case, that's the matrix ends up being 1 minus 1 plus square root of 2 times I. I'm going to go very slow here. 2, -1, and then same thing. 1 minus 1 plus square root of 2 times I. Okay? This is the matrix P minus lambda times the identity, and if we want to augment it with zeros, we can do that. Okay? Now, this is where I'm going to go back to that fact. The fact is that when you have this 2 by 2 matrix, okay, what 2 by 2 matrix? This 2 by 2 matrix right here. What we know about this 2 by 2 matrix is that it has determinant 0. You can go and check that. You can take the determinant of this matrix, do the complex arithmetic. I swear to God, it'll be 0. That's the whole point about finding the characteristic polynomial and finding its roots. The roots obviously make the characteristic polynomial equal to 0 when plugged in, right? So when we plug that eigenvalue, that root of the characteristic polynomial, into the matrix P minus lambda times the identity, then of course we're going to get something with determinant 0, okay? So assuming that we've done all of our computations correctly, and that is a big if, that is a big assumption, but assuming that we've done that all correctly, here's what I can conclude. This row right here is a constant multiple of this row right here. That's always true about a 2 by 2 matrix with determinant 0. I'm going to remind you of this fact because it's useful. Remember, if A is 2 by 2 and the determinant of A is 0, then the rows are scalar multiples of one another. Multiples of each other. I'll just write it like that. Keep it short. Why is this so useful here? It's so useful because we know that we don't need to think about that second equation, that second row. We can operate simply from the first row. Does this make sense? Like, I can ignore the second row altogether and just conclude from this that what must be true about this eigenvector is that 1 minus, and I'll simplify this in just a second, but just relax, okay? 1 minus 1 plus square root of 2 times I times V1 plus 2V2 is equal to 0. And that characterizes my eigenvector V1, V2 completely, okay? This equation. Any V1 and V2 which satisfy this equation, which is non-zero, will be an eigenvector of my matrix P. Okay? So in particular, this equation is equivalent to, just simplifying now, negative square root of 2 times I times V1 plus 2V2 is equal to 0. Okay? And so what this suggests is that if I add square root of 2 times I V1 and divide by 2, that V2 is equal to square root of 2 times divided by 2 times I V1. And I like writing this to make my high school teacher mad. 1 over the square root of 2 times I, v1. Because I like radicals in my denominators. Okay. Sorry, Mr. Leger. Okay, anyway. Yes. I'm not actually sorry. That was disingenuous. So now what I can do is pick any non-zero value for v1. Let's take v, our eigenvector v will then be, so I'll take v1 to be, well, maybe I'll denote this, v1, v2. I'll take v1 to be, I don't know, 1. I could take it to be square root of 2, by the way, also. Maybe I'll do that. Let's take v1 to be square root of 2 instead, because that gets rid of fractions. It doesn't get rid of square roots. I don't think I can get rid of that in my life. But then what's v2? v2 is I. Do you see that? Because if, look here, if v1 is square root of 2, then v2 evidently is 1. Or I'm sorry, I. My bad. I. Okay? So that's my eigenvector. Great. So now, I've done this step right here. I've found the eigenvalues. That's great. I've found the eigenvector. That's great. Next thing that I'm going to do is I'm going to form x equals v times e to the lambda t. So my x, and this is a complex valued x, and you'll see that manifestly come out, is square root of 2i times e to the, what is lambda? I forgot. Oh, there it is. I'm doing good bookkeeping, so I can never mess this up. It's 1 plus square root of 2 times I times t. All right? And the point is, this is a complex valued solution. When you plug in numbers for t, real numbers, you get out complex valued vectors, vectors with complex numbers in it. And that's just not what we want. What we want are real valued solutions. So I've done this step here, and the fact that I'm foie gras down your face is that if I compute the real part and the imaginary part of this purple thing right here, this guy, if I compute the real and imaginary parts of this guy right here, then according to this fact, which I'm foie gras down your face, these are real valued, linearly independent solutions. There's a lot happening there. Again, foie gras, steel pipe, accept it, okay? Fattening of your brain and such. So that's what we're going to do next. We're going to find the real and imaginary parts. Real part of x and the imaginary part of x. Okay, how? Well, this is where, remember the guy with the bag on his head? Euler comes in clutch. Okay, so let me remind you about Euler's formula. Or Euler's identity, whatever. Which tells you that e to the I t is equal to cosine t plus I sine t. Unbelievable, this. Absolutely gorgeous. Okay? You need to hold this close to your heart and never let it go. I was about sorry. I had an intrusive thought for a moment, but I thought better of it because I was gonna truly humiliate myself in that moment. Okay, great. So how are we gonna use this? What we're going to do is manipulate this x. It's going to be long, but we're going to manipulate this x to get it into a state where we're segregating the real parts and the imaginary parts. We want to get all the bits involving I in one term and all the bits not involving I in its own separate term. Okay? How? Good question. So I'm trying to think what the my efficiency brain is working right now. One thing I should do is, okay, sorry. I'm not actually sorry when I say that. That's some kind of tick that I have. Okay, this becomes, by Euler's, well, by simple considerations of the exponential function, this first of all becomes square root of 2 times I times, now this I can split up, this exponential right here, I can split up along this plus. And what I get is e to the t times e to the square root of 2 I times t. Okay? Great. And now the point is that I can use Euler's identity on this guy right here. Now, the fact that it's an identity means that if I was to replace t here by square root of 2 times t, it would still hold, because it holds for this blue box holds for literally all t. That's what an identity is. It's an equation which is true no matter what the value of t is. So it's true if that t is replaced by square root of 2 times t. So what we get then is square root of 2 times square root of 2 I e to the t, and then we get cosine of square root of 2 times t plus I sine square root of 2 times t. Okay? Great. Let's keep going. Remember, my goal here is to segregate, make a big ass term with I involved and another term that doesn't involve I. So I think what I'll do is fold in the e to the t. Just go slowly here. Fold in, distribute the e to the t like this. Bang, and then bang like this. So I get e to the t cosine square root of 2 times t plus I times e to the t sine square root of 2 times t. Good? Yeah. Now I'm going to ask myself, okay, maybe I'll do it like this. I'm going to, do I really want to do it like this? I think so. I'm going to rewrite this vector. You know what? No, this is going to hurt your feelings. What I'm going to do instead is just distribute this vector, right? Distribute this piece over here into this vector. I'm going to make a big ass vector, in other words. So big vector here. I'm going to have square root of 2 times e to the t cosine square root of 2 times t plus square root of 2 times I times e to the t sine square root of 2. Why did I say 2? Square root of 2 times t. Okay? And then I multiply this whole thing by I. So I have I times e to the t cosine square root of 2 times t plus, and now look, this I and that I get married and become a minus sign. Minus e to the t sine square root of 2 times t. Don't sleep on that minus. Okay? Now I can, I think, pretty easily break up this vector into a real part and an imaginary part. Watch. The real parts are going to be this square root of 2 times e to the t cosine square root of 2t. Cool. That's going to be the top entry. The bottom entry will be negative sine square root of 2 times t. Oh, wait, my bad. I messed up. E to the t sine square root of 2 times t. And you might be concerned, except remember what I'm going to do now is write another term involving the I bits. So this is going to be plus I times, and I'm moving the I outside, okay, the vector. And I have upstairs square root of 2 times e to the t sine square root of 2 times t. And then downstairs I have e to the t cosine square root of 2 times t. What am I doing here? I'm just looking here at this term and that term, noticing those are the bits that involve I, okay? Putting that I outside the vector and then just, yeah, accounting for them correctly. Okay? Point. The point is that this part right here is the real part of x, and this part right here is the imaginary part of x. And if you go back to my claim, my foie gras claim, which is sitting right here, then that states that those bits, the real part and the imaginary parts, are real valued, linearly independent solutions to this system. If you believe all that, then you know that you can take a superposition of those and arrive at the general solution. And that, indeed, that's going to be our conclusion. The general solution is x equals C1, maybe I'll go slow, C1 times the real part of x plus C2 times the imaginary part of x. Okay? But now I can just copy, which is C1 times, I'm so tempted to just, oh my god, it's too tempting. Duplicate, move it here. Oh, there's all this other purple junk everywhere that I grabbed. Oops. This, and there's all this red junk here. And then there's all this here. And I need to get rid of this and that, and then put plus C2 times this, and then I win. Do you see that? And it still looks a little ugly because I've got purple stuff here, so let me fix that. And I claim that this is not only right, but I saved time by doing that stupid thing that I just did. Maybe that looks confusing. C1 plus C2. Does that look better? You get the point, though. The prescription to follow is this one right here, which we just, and we did all 4 steps here. All right? Solve the system. You need to find the complex conjugate pair of complex eigenvalues. Okay? Find a complex eigenvector associated to one of those eigenvalues, form the ansatz, x equals v e to the lambda t, and then use Euler's identity and careful manipulation to obtain the real part of the solution, of the complex valued solution, as well as the imaginary part. Okay? That's it. That's really all there is to say about this. Yeah, maybe in the next one we'll do one more example. It shouldn't take too long, but I think it's worthwhile doing at least one more just to see it all play out. All right, so long. See you in the next one.